First question, what is the sum of the coefficients when the equation is balanced with whole numbers? Okay, well, let's see what we are given. CHO and CHO. We've got 8 and 1. We've got 18 and 2. And 2 and 2. So let's make the carbons equal. We'll add an 8 there. That will make this 8. But it will also change the oxygens. So then we'll have 9 oxygens. Cool. Well, then let's make the hydrogens equal. We'll add a 9 there. That will make that 18. But again, it will also change the oxygens, and we'll have 17 oxygens. That cannot be divided into 2 equal parts, which is what we'd have to do. So had it not said whole numbers, we could have just done 17 divided by 2, had this been a fill in the blanks with the correct numbers. But because it is whole numbers, so this would be 1, we will have to times everything by 2. So this becomes 2, this becomes 17, this 16, and this 18. So then the answer will be C, 53. Question 2. Okay, quite a wordy one. So what we know is we'll be using this equation. Now, what is this equation? Maybe you've forgotten what it is. Maybe you can't remember the triangle, which way around it goes. It doesn't matter. You're given the units. So it says 22.7 decimeters cubed per mole. So we know that the decimeters cubed will be at the top. Now that represents volume. The moles have to be at the bottom, and obviously what we have left is the 22.7. And there we have our triangle. Didn't need to remember it. Right, so we'll have to use that. Okay. Because we're working out volume, we know that we'll need to be timesing the moles by 22.7. But now what moles do we use? Moles of calcium carbonate or moles of hydrochloric acid? We use the one that's limiting us. So looking at CaCO3, moles of that will be mass over molar mass, which is given here. So that will be 0.01. Then we have HCl moles, right? Well, that's where we use the equation concentration times volume equals moles. Okay, well, this is in centimeters, so we'll have to convert it to decimeters cubed, that's right. So then we end up with 2 times 20 divided by 1,000. That will get us, so you'll have to do this without a calculator, so let's just try and work it out. Let's cancel those zeros. 2 divided by 100, 0.02. But because we're timesing it by 2, it will be 4, 0.04. Right, so which one's limiting? The calcium carbonate, right. So then we know it will either be C or D. We're trying to work out the maximum volume of carbon dioxide. The stoichiometry, we've got 1 there. Since we're using the calcium carbonate, we're looking at this. There's also 1 there. So we don't need to times by 2, which means it will be C. Next one. Which factors affect the molar volume of an ideal gas? Pressure, temperature, empirical formula. Okay, well, we know empirical formula won't affect our volume of an ideal gas. It'll be pressure and temperature, and that will be A. Which electron transition emits radiation of the longest wavelength? So because we're always emitting, it's called the emission spectrum with the IB. So when do these electrons emit radiation? It's when they come back down, when they fall down to lower energy levels. So you will never ever be selecting the arrows going up. Those will never be right. So already gives you a 50-50 chance. If we use Richard Thornley's big jump, big energy, small wavelength, we've just got to do the opposite. Small jump, small energy, long wavelength. And that will give us C. X, Y, and Z represent the successive elements, neon, sodium, and magnesium, but not necessarily in that order. Okay, so let's get our periodic tables out. So looking at the periodic table, neon, sodium, magnesium. Okay. First ionization energy, that's all about the energy required to remove the outermost electron. So neon is stable, it's a noble gas, so that will require the most energy to remove one of its outer electrons. It will be a real struggle. So then we can safely assume that X is neon. So next we've got sodium and magnesium. Which one will require more energy? More energy to remove that outermost electron? Well, that will be magnesium. Magnesium will need more energy. Okay, well then Z will be magnesium. So that leaves us with sodium in the middle. Now the question is not what is the order of increasing ionization energy, but actually of increasing atomic number. So the first will be neon, so that will be X, so A or B. Then we'll have sodium, so that's Y, and that leaves us with A. Which property increases down group 1, the alkali metals? What I did with all the trends for paper 1, when you needed to just quickly remember whether it increases or decreases, is I created a little table for myself that I memorized, and I would just write that down every time. So we've got A, E, I, where A is atomic radius, and the last I is ionic radius. So you know that the radiuses are on the ends. As you go across, the radii decrease, everything else increases. As you go down, the same A, E, I, the radii increase, everything else decreases. So I'd write that down really quickly and then work it out. So which property increases down group 1? Well, that will be either atomic radius or ionic radius. So that will be A. Which element is a lanthanide? Right, so you've just got to know your periodic table. The lanthanides are the first row at the bottom, so that will be TB. Ammonia is a stronger ligand than water, which is correct when concentrated aqueous ammonia solution is added to dilute aqueous copper 2 sulfate solution. Okay. The d orbitals in the copper ion split. Well, yes, they do, but that's not exactly relevant. They do with water and they do with ammonia, so nope. there is a smaller splitting of the d orbitals. With ammonia, you have a bigger splitting of the d orbitals. The stronger the ligand, the bigger the splitting. So it won't be that. Ammonia replaces water as a ligand. Yes, it does. It does replace water as a ligand. So that will leave us with C. How many bonding electrons are there in the urea molecule? The trick here is to remember that the nitrogens are each attached to 2 hydrogens. So then you'll get 4 extra. We've got 1, 2, 3, 4, plus the other 4, 8, but that's pairs. We want bonding electrons, so that will be 16. Which does not show resonance? Well, we know that ozone shows resonance, benzene shows resonance. So then you've got a 50-50. If you know your organic, you'll know that CH12 is just a hydrocarbon, so it won't be showing resonance. Whenever you have ions, it's most likely polyatomic ions, it's most likely that they will have some resonance. Which metal has the strongest metallic bonding? Well, the smallest atom will be lithium. So that means it's got a short distance between the nucleus and its delocalized electrons. If you also think about the melting point, going down group 1, it decreases. So melting point decreases. So there's less energy required, weaker bonds. Therefore, our answer will be A. Which is the first step in the CFC catalyzed destruction of ozone in UV light? Well, our first step will be to obtain a chlorine radical. So the only one it could be is B. We need to obtain that chlorine radical. Which statement is correct? Sigma bonds are formed only by the combination of s atomic orbitals. No. It's actually S and P, overlap between S and P, and that's a head-on overlap. Pi bonds can be formed in the absence of sigma bonds. No, they cannot be formed. So every single bond consists of 1 sigma bond. A double bond will be made up of 1 sigma and 1 pi. So that won't be right. Pi bonds are formed parallel to the axes between atoms. Yes. They are an overlap of orbitals in a side-by-side manner. So you've got the electron density concentrated above and below the plane of the nuclei of the bonding atoms. So it will be C. Why is it not D? Pi bonds are formed only by the combination of hybrid orbitals. Well, no, hybrid orbitals will always overlap head to head, so that will form sigma bonds. What can be deduced from this reaction profile? Well, it's exothermic, we're releasing energy, we're going this way, so it will be either A or C. The reactants are less stable than the products. Why, yes, they are. They've got way more energy. What can be deduced from the fact that ozone absorbs UV radiation in the region of 340 nanometers and molecular oxygen, so that's just O2, in the region of 242 nanometers. Right, the bond between atoms in a molecular oxygen is a double bond. Oh, well, that is true, but you cannot deduce it simply from what the question has told us. The bonds in ozone are delocalized. Yes, they are, but again, we can't deduce that just from the question. The bonds between atoms in ozone are stronger than those in molecular oxygen. Well, that's untrue. So that leaves us with D. The bonds between atoms in molecular oxygen need more energy to break. Next one is a Born-Haber cycle for potassium oxide. Which expression represents the lattice enthalpy? So the way I like to think about this is this side going up there, it's got to equal this side. So if we work out 1, we can be pretty certain that 2 has to equal it. Okay. So following the arrows, this is going down. We're turning it the other way around. We're going up. So it'll be a plus. So that leaves us with B or D. Everything in B and D is the same aside from the very end. This is plus 612 and this is minus 612. We're going with the arrow, we're going up, it's plus. So that will be B. Which ion's hydration energy is the most exothermic? So hydration enthalpy is defined as the enthalpy change when 1 mole of a gaseous ion is solvated by solvent molecules. So the way that's shown is X minus, that's our ion, in a gaseous state, plus aqueous gives us an aqueous ion. So gaseous ion turning into an aqueous ion. Okay. Now, with small ions, you get very strong bonds, which means you get a larger exothermic energy change. The other thing to mention is the high charge magnitude. So with a high charge magnitude, you'll get stronger bonds and again, greater exothermic energy change. The term charge density is occasionally used to refer to the charge volume ratio of an ion. So high charge density is associated with strong bonds. The one other thing I'd mention here is the Hess cycle that you might encounter in exam questions, especially in paper 2, high level, the enthalpy of solution. So it's a Hess cycle with solution with lattice and hydration. And that shows you the relationships. So that might help you in memorizing the definitions for each of these enthalpy changes. Cool. Moving on to the next one. These next 2 questions are both about the same reaction. Which change does not increase the initial rate of reaction when calcium carbonate is added to excess hydrochloric acid? Right, so we are wanting to not increase the initial rate. We don't want to increase the initial rate. Decreasing the size of the calcium carbonate particles, well, what that will give us is an increase in surface area, which will lead to a faster reaction. So it won't be A. Increase in the temperature of the reaction mixture, well, that would just mean that the particles on average have more kinetic energy, so it won't be B. Increasing the concentration of hydrochloric acid, keeping the volume the same. When increasing the concentration will also increase the rate. D, increase in the volume of hydrochloric acid, keeping the concentration the same. Yes. So that won't increase the initial rate. Which methods can be used to monitor the progress of this reaction? Change in color of this reaction mixture? No, that's usually the case when we've got iodine. Then you can measure a change in color, change in mass. Yeah, you can measure a change of mass of this reaction mixture. Change in volume. Yes, we've got the carbon dioxide gas there, so you can measure the change in volume of gas evolved. So that will be 2 and 3, and that will be C. Which is true of the Arrhenius plot of ln K against 1 over T? This is the same as Y. Now, knowing this, we can eliminate some of the options. For example, the intercept on the y-axis is the frequency factor A. Well, we know that this here is the y-axis intercept. So we know it's not A, it's actually ln A. Therefore, it can't be D. The intercept on the x-axis is the activation energy. Well, no, that can't be true. The activation energy can be determined from the gradient. Well, yes, it can. We're looking here at M, the gradient, so it'll be B. The graph goes through the origin. No, the graph doesn't go through the origin. I will insert a photo now. Next question. A species that is 0 order does not take part in the reaction. It does take part in the reaction. It just comes after the rate determining step. That's not right. A catalyst does not take part in the reaction. It does take part but is unchanged. Reactants in a fast step before the slow step are included in the rate expression. Yes, so the rate expression includes everything up to and including the slow step. Anything after the slow step is not included, so it cannot be D. Which variable affects the equilibrium constant Kc? The only variable that affects it is temperature. Temperature, nothing else. Kc is only affected by temperature. So it's very typical to be asked about a reaction and to have to write about the change in Kc. And many times the answer would be no change because temperature is the only variable that affects it. Components X and Y are mixed together and allowed to reach equilibrium. The concentrations of X, Y, W, and Z in the equilibrium mixture are 4, 1, 4, and 2 mole per decimeter cubed, respectively. What is the value of the equilibrium constant Kc? Well, if I just write it out again, so X is 4, Y is 1, W is 4, and Z is 2. Kc will be products over reactants. So that will be 4 to the power of 2, because we've got this 2 there, times 2 to basically the power of 1 over 1 to the power of 2 times 4 to the power of 1. So of course we can take the 1's away. That will leave us with 16 times 2 divided by 4. That's 32 divided by 4. So that is 8, which is D. Which of the following does not react with dilute hydrochloric acid? We're given an extract from the activity series. Anything below hydrogen won't react, so that leaves us with copper. Which of the following is correct? A weak acid is a proton dot. A weak acid is a proton. A weak acid. Oh my goodness. A weak acid is a proton donor, and its aqueous solution shows good conductivity. Well, no, it shows bad conductivity. So then it will be B. Yeah, so the first thing is the idea of an acid being a proton donor, and then it tests your knowledge of conductivity. Which type of bond is formed when a Lewis acid reacts with a Lewis base? Well, you don't know that it will be a dipole-dipole. That's also not a bond, that's an intermolecular force. Hydrogen bond, well, that has to have hydrogen, nitrogen, fluorine, one of the NOF. So you don't know that that's the case. Double bond, again, don't know that that's the case. So it will just be a covalent bond. What is the order of increasing acidity of the following acids? So the trick here is you're given two tables, one's the Ka, one's the pKa. So the trick here is the bigger the Ka, the stronger the acid, and the smaller the pKa, the stronger the acid. You need to watch out for the powers. So which one has the bigger Ka? Chloroethanoic or ethanoic? It will be the chloroethanoic. So that's 1, that's 2. And then on the other side, the smaller the pK, the stronger the acid. So this will be stronger, this will be weaker. So increasing acidity will be ending with the strongest acids. So we can't be starting with chloroethanoic or hydrogen fluoride. So it won't be A, it won't be C. Chloroethanoic for B comes in second. That's not right. So it will be D. Which element is reduced in the following decomposition? Let's zoom in a little bit. So, first compound, we've got the ammonium ion. That will be +1, but in total will be +2. We've got the oxygen, which is -2, but in total will be -14. So -14 +2 -12 divided by 2 means the chromium will be +6. So let's see how everything's changed. Well, the nitrogen is now 0 because it's an element. The Oxygen still minus 2 times 3 minus 6. So the chromium's changed because it now must be plus 3. So reduce, what's being reduced? Well, that's the chromium. Which of the following is not a redox reaction? Anything that contains an element will be a redox reaction. So there's an element there, even if it's a diatomic molecule, such as Cl2, I2, H2, still counts because they're still 0. So they won't be found as elements on the other side. So clearly here, it won't be 0 anymore. So it won't be A, there's an element. This has got elements, won't be B. C has got elements, won't be C, so it has to be D. Next one, we're changing the 0 potential reference electrode from the hydrogen to a zinc one. Right, to a zinc one. Because this is more of an oxidizing agent, we follow the same protocol, which is plus minus minus 0.76, which will add up to 1.1. What are the relatives volumes of gas given off at ENF? During electrolysis of the two cells in series, assume all electrodes are inert. So looking at the positive electrode, starting off with that, we'll be picking the negative ions. So which negative ions are we in between? Because it's an aqueous solution, we've got water involved. So aside from SO4, 2 minus, we'll also have OH minus because the ions of water are H plus and OH minus. We know that when water dissociates, it dissociates into those two. So which one will be most easily discharged? That will be the water, or rather the OH minus, the hydroxyl ion. Well, why is that? Because salts are never oxidized. So sulfates will never be more easily discharged than hydroxyl ions. Nitrates as well, they won't be oxidized. So if you're picking between a salt and a hydroxyl, it will always be the hydroxyl. There are other cases where you've got concentrated dilute and you've got a hydroxyl with a group 7 with a halogen. So that's different. But for the purpose of this, we'll be picking the OH minus. Now, what about the other side? So we're looking at the negative electrode. So we'll be picking one of the two positive ions. So what do we have? Well, again, it's aqueous. So we'll have the positive ion of water, which is H plus, and the SO4 minus again, that's the negative, and the positive will be the H plus again. So obviously it will be the H plus. No picking to do that. Right. Now this is quite mean because what you basically need to remember are the equations from the data booklet. So the equation for the OH minus is 4. And for the hydrogen, now because we're looking at the ratio, what we must do first is balance the electrons. So we're going to need to times everything here by 2. So what do we get? We get 4 hydrogen ions, 4 electrons, 2 hydrogen molecules. So in terms of our products of gases, because that's what we're looking for, where are our gases? We've got O2, 1O2, and we've got 2H2. So then the ratio will be 1 to 2. Which functional group is present in paracetamol? Carboxyl. Well, that's COOH. We haven't got that. Amino, we haven't got that. Nitrile, no, but we do have a hydroxyl right here. It could be said that this is a phenol. So if you ever get a phenol option, that's a hydroxyl attached to a benzene ring. But that's not an option, so it'll have to be D. Which describes the reaction between a halogen and ethane. So that's the free radical substitution mechanism, A or B. And the bond fission in that is homolytic. Which compound contains a secondary carbon atom? A secondary carbon atom. So that atom needs to be attached to 2 other carbon atoms. Two other carbon atoms, right. Well, already I can rule C out because this carbon will be attached to 3 methyl groups. So that's 3 other carbons. We're looking for 2 other carbons. This carbon here, it's attached to 2, but then there's another one on the other side. So it can't be B. Here we've simply got methyl group attached to a carbon attached to chlorine. So that's not going to be secondary, which leaves us with A. So if we draw out the structure, CH3. So this carbon here is attached to 2 other carbons. Which pair of isomers always shows optical activity? That will be the enantiomers. Enantiomers show optical activity. Which compounds can be reduced? C2H4, so that's ethene. Yeah, that can be reduced to ethane. Ethane. Second one, carboxylic acid, can be reduced to, that's right, primary alcohol. And then we've got an aldehyde. That can be reduced to also a primary alcohol. So that would be D, all of them. What's important to note here is that we are starting with benzene, not nitrobenzene. So it's actually combining 2 mechanisms into one. So starting off with the electrophilic substitution with benzene, where we are adding NO2 to benzene to turn it into nitrobenzene, what we need there is concentrated nitric acid and concentrated sulfuric acid. So already, if you just know that, it will be C. So during the mechanism for the first bit, and then at the end, I would just add H2SO4 and just say catalyst regenerated. Right, so then what about the reduction of nitrobenzene into phenylamine? What can be deduced from the following H&MR spectrum? There is only one hydrogen atom in the molecule. No, we're not told that. There's only one hydrogen environment in the molecule. Yes. So every line represents a hydrogen environment, a different hydrogen environment. So that's what we're told there. The molecule is a hydrocarbon. We don't know that. There is only one isotope in the element. Well, we would need the mass spec to figure that one out. So we'll stay with B. What is the graphical relationship between N and T in the ideal gas equation, all other variables remaining constant? Well, if we were to rearrange the equation, it would be N equals PV over RT. So as T increases, N must decrease. So then A and C can be eliminated because we've got an increase there and we're looking for a decrease. The answer will be D. What B represents is 1 over T. 1 over T. Which technique can be used to identify bond length and bond angle? H&MR spectroscopy. No, that's about hydrogen environments. IR spectroscopy. That's all about functional groups. Mass spectroscopy. That's the molecular ion peak. That's isotopes. X-ray crystallography. Yes. So that will be D. X-ray crystallography, interestingly, also tells you which enantiomers, which enantiomer you have. And that's the end of this paper.